Bismillahirrahmanirrahim. Welcome to another episode of Network Analysis on Easy Learn. And let's start the episode 12. And first of all, let us discuss precisely about the previous discussion. We are discussing the final parameter, means the circuit interpretation of the we are discussing inductance parameter. So it is understood. We are discussing the we are going to define a relationship for the current in terms of the inductance parameters, but due to the time shortage we were not able to define and finally calculate a precise relationship for the here psi is equals to n integral this equation. This is what we left off last time, and so we are going to discuss this same equation and going to recap this first and then continue. This equation here is actually just substituting the values here of the the flux, and then we get this equation. Here we just extract the current I, and just I said that if you want the proof of this, how this actually I comes outside from this integral jurisdiction, so this I proof is available on the Facebook page, and if you didn't found, remind me, I will upload again. So the integral equation of the above equation, sorry, integral parameter here, this is a mistake. The integral parameter, this parameter from here, that is started from this first integral. This integral parameter has the whole jurisdiction. It covers from this and ends to ds. So I am interested in this whole integral parameter. The integral parameter of this above equation can be calculated mathematically. If I have all the values like the flux linkages and the current, then easily I can calculate whatever it is. But main thing is, if I have the values, if I don't have the values of these, it is very difficult for me to calculations and for pi and other things. So this is actually, this integration parameter is our main thing, and it is called the inductance parameter. This is the one thing that you need to keep in your mind, that this is called inductance parameter or coefficient of inductance. This is the same thing. If I said coefficient of inductance or inductance parameter, it is understood, same thing. So psi is equals to n integral this equation. N is actually the number of turns of your what you will call inductance. For example, here if I am able to draw here, this is our solenoid and it has different number of turns. Sorry, I was not able to draw. Actually, this is that means that number of turns, and if air current flows, like current is flowing, we are able to have a finite amount of the magnetic flux lines. This is called the flux linkage. If in terms of the network analysis, whatever we are discussing it here, we actually defined in the previous discussion that why we call it as a flux linkages. It is due to in a system, and there are two cases now: flux linkage of the system 1 and the flux linkage of the system 2. There are the two systems. Like in the case of the transformer, there is a first coil and the current I1 that is flowing in the system 1, and the flux that is produced in the system 1 is called the phi1, or in our case, if we want to discuss the flux linkage, then we can call this psi1. But if it can produce or linked with another system, then we will call it as a system 2. Like here, in case of the transformer, there is actually no direct connection. It is only the one connection, that is we called here, it is I2, and the flux linkage inside here, it is the psi2. Like here, if this is the case 1, when a current flows in the solenoid, and due to the flow of this current, a flux produced, and this is actually in a single system. Means the coil is connected to a system and the flux is due to this current and not linked to another system. If we have a system like that, the current there is a flux, and the flux is in the same system in which due to which it is produced. Means the current is the reason of the production of the flux here, and the flux is still here in this system. Then we will call it as a letter L, which means that this is a self-inductance. As the name indicates, that self-inductance means the inductance due to the self production, self-produced. So this case, then if suppose that we have this type of the system in which the flux is produced due to our case like self-inductance, solenoid case, simple, then this inductance parameter, the coefficient of the inductance of this equation here, it is replaced by L. Remember that this N usually can be ignored because it is understood and it is only written when it is given in our equation, in our when it is provided in the in numerical, then we will use this N. But if this is not given, we will ignore it, and our formula, if it's case of the self-inductance, suppose L, our formula actually becomes psi is equals to Li. You know, this whole parameter is now replaced with L, and N, as I said, you can ignore it or just it is understood. So this is Li. This is the equation number 2. So let's discuss the case number 2. There is another case, like if current is flowing in a system and the flux is produced, but this flux is linked with another system, then this is called the mutual inductance, and it is represented by the letter M, which shows that the current that is flowing in this system, psi1, it links to another system. Due to the current one, the flux is introduced in another system. Actually, this is the case of the transformer, but right now we don't need to go into the details that how it is produced, how it is details. If you want details right now at this time, you can go to the introduction to electronics part 2, where with this season 4 part 2, where you can easily find out all the details about the flux, the links, and transformer details, whatever you want. But right now here we are not interested in this right now. This is not the matter of the discussion because already time is very short. So this is the two system involvement. One is the source and other is the receiving end. Then we will call it as a letter with M, which means that the inductance, but due to the mutual cooperations with 2 or 3 systems, we will going to discuss this case and represented by the letter M. So inductance and this overall parameter, coefficient of the inductance parameter, can be now replaced with the letter M. So our equation number 1 again, in case of the mutual system, becomes mutual inductance becomes Mi. So this is replaced with M. So this is equation number 3. But remember that we will we can replace M with L with M in case our formulas are actually, we are going to discuss one case, that is the self-inductance. I throughoutly use LL in our formulas, but if we later found numericals that are the conditions are mutual inductance, then we can replace the letter M with the M, because there is a mutual inductance which can be replaceable. But right now, because we can only discuss one case here, it is not possible to discuss both cases simultaneously. I can write the line in center half the page, divide the page, and then write one at the one side and the other on the half on the second half portion of the page. But it's easier to discuss the one case of the self-inductance L. Okay, this is interchangeability, so don't worry about this. Again, note that the similarity of this equation psi is equals to Mi, psi is equals to Li, equation number 2 and 3 are again means that in equation in the previous episode 11 we discussed a very beautiful relation of this equation with Q is equals to integral I. Same is the case in a simple format. Q is equals to CV. In the capacitive parameters, we introduce this formula Q is equals to CV. Actually, this and this is same, but in case of the integral, in case of the inductive system, we are going to use this equation. But if we have a capacitive system, we need to use Q in terms of CV. Q is the charge that is here. We are going to use the flux linkage. And M, you know, this is inductive system that is representing the inductance here. Either it is a mutual or a self, while the capacitance has no such case, so it is just written as a C. And here it is representing the voltage, while in our today's case, the current is the main issue that sorry, not an issue, main theme that we are going to discuss. Actually, the whole discussion is, in the case of the inductive, becomes opposite. Voltage is now replaced with the current, capacitance replaced with inductance, charge replaced with the flux linkage. So this is the new terms, but the similarity of this equation is the same. Whatever we discussed there, we will discuss again here. So it is now much easier for me to explain the things here in today's discussion, in today's episode, if you already understand the previous episode. So it is much easier for me. Now substituting the equation number 2 in Faraday law. Actually, this equation number 2 is the same as the equation number 3 in case of the self or the mutual inductance. So let's just discuss the self-inductance case. So this is actually flux. Now first discuss the Faraday law. We already discussed the Faraday law. EMF is equals to d flux. D psi means derivation of the flux with respect to time, change in the derivation. So just substituting the value, replacing this psi with our inductance parameter. So it is the equation number 4, derivation with respect to time Li. If inductance does not varies with respect to time, it means it is a constant. We have an inductor that does not varies with respect to time, its value, then we can say V is equals to L. We can write it outside this derivation portion, L di over dt. This is called equation number 5, inductance as constant. Using this equation number 4 or 5, this is actually the same equation. If we have a constant flux, actually don't be confused in this. Just say using the equation number 4. Sorry, you say equation number 5, because we are going to in a same rhythm. Just forget about this. V is equals to L di over dt if we have a system in which usually our flux is constant. So we are going to discuss this case when our flux is not changing but current is changing. So flux is constant. Just we are writing it outside the derivation. We are taking as a constant value. So then right now we want to discuss and want to introduce a specific relation of the current with the parameter of the inductance. So discussing the current here, if we want to interested in the current, just we need to integrate this equation number 5. What do we need to do here? Actually this is the same thing, equation number 5. Li is the, if L is constant, you can just write it as it is. D is goes to di, and dt is here in the dividend. And if we going to separate this by the cross multiplication, it will go to in the multiplication side with the v in the numerator. Taking the integration of this equation, actually integral of the v dt and L is constant di, applying the limits minus infinite to the present time t, as in the case of the previous in the capacitive system we did. So 1 over L minus infinite to time t v dt is equals to I. How? Actually this L is here in the multiplication side, so it will come here to the other side. It is in the dividend, 1 over L. This is the main thing. This is the inductance here. Okay. So integration of the di is the I raised to power 0, integration of the I raised to power 0, actually 1. So integration of the 1 with respect to current is the I, simply I. So again writing this all the parameters, just left hand side to the right hand side replacing, and the this I to the here. Nothing, I'm not changing any parameter, just writing and in a standard form. I is equals to 1 over L integral minus infinity to t v dt. So this is the final parameter that we want to define in today's episode, and ultimately I got succeed in and hopefully you understand this. So now we are going to say and define what this is. This is the actually the current in a system of inductive system. Current changing in the inductive system and the behavior of the current in inductive system. Now just discuss that there is an uppercase Greek letter. Now we are going to introduce this, like half t, or just the 7 that is written in the replica of the 7, the mirror image of the 7. Like this is called the Greek letter gamma. Actually we use this many times. Some of you may be unfamiliar with the this letter, this is the uppercase letter of the gamma. This is the lowercase Greek letter gamma. We are like R. We definitely used many times this letter. But this letter is now used to represent 1 over L. That is the inductance here. In MKS unit system, the inductance or the standard unit is actually Henry, which is named after to honor the American scientist Joseph Henry, who is the founder of this system. Okay, so as you know, in case of the capacitive system, we discuss the conditions that are feasible to our system. We exclude all the possible cases that are not suited to our case, and which makes our system to blast, to maybe not accessible, or you can simply say infinite to shoot system. Giving you the reference of episode 9 when we discussed this thing, Q is equal to CV. At episode 9 we discussed that if the voltage here in the voltage or the product overall CV changes instantaneously, means if voltage is changed, then it means that overall CV changed, product changed. If product is changed suddenly, which means that if it is increased, the current, the charge also increased. Just to recap the concepts we discussed there, I wanted to just show you here that if we have a system like that, if we in a system, if it is suddenly increased, like a thing that is suddenly increased, this is not feasible. If the voltage is going on like this, I'm drawing, this is okay, this is fine. But if the voltage at a specific time suddenly increase in such a way that we call as a impulse function, if you remember exact, this is what I exactly used the word at that time. The impulse function will be discussed and introduced in the network analysis later on, not right now. So which means infinite current, because if the product is increased, CV is increased, which means that charge is suddenly increased in a system at a specific time. If the charge is increased, which means that the infinite current. How? Because I is equals to dq over dt, the derivation of the charge with respect to time. If charge is increasing suddenly in an impulse function, the current will be infinite, but we are not interested in those cases which make our system infinite. So we are going to exclude the impulse function in our discussion right now. We will discuss these all cases, but after episode 100. Same is the case of the inductive system. Indeed, such relationship can be found using equation number 5 of episode 11. This is the previous episode actually, when we started the actually half of the part of the capacitive parameter, half portion of the circuit interpretation is discussed in the previous episode. So this is actually the same topic continuously using. So equation number 5 of episode 11 is the relevant to our discussion. So if we are going to use the previous equation number 5 of the previous episode, you will find this psi is equals to integral minus infinity to t v dt. Actually, as in case of the capacitive system, we did that this is a very long durational time period, that prior to the switching time period to the present time. This limit is generally used, but how we can separate this limit into two portions, to the prior to the switching time and to the present time. Prior to the switching to the present, prior to the switching to 0 time period, and then 0 to time present. So these are they are the two times that this where we can separate. Like actually, they first of all, there is a time period like this. This is a time we said that this is before, prior to switching. We don't know about this time, and this is a time where we are present right now. And this is our circuit. Suppose that this is our circuit. We have a circuit of this type, and if in this circuit we are going, this is a switch, sorry, I was not able to, this is a switch, and if we are not turning on the switch, this is called all the time before my turning on or closing the switch is known as, before all the time is taken as minus infinite. When I turn on the switch, this is, for example, here I turn on the switch, this point is known as t is equals to 0. So there are the two times from time frames. Actually, this time that is called prior to the switching, and this is called after switching. After switching time period is very important. We are interested in this time period, not in this, because it is actually given. We can't calculate actually this time period, so that is the main reason it is given. This time period is called minus infinity to 0, and this time period is 0 to present time. So again, this time period is given, so, and is a constant value. For example, the value it is given in the question is, let's suppose 40, it is given, so it is constant. So psi naught, when we simply write a small 0 here in the subscript, it means that psi naught, and it is a constant value. I naught constant value, V naught constant value. Whenever we are going to use these type of terms, it means it is a constant value term. Psi is equals to psi naught plus integral 0 to t v dt. So this is the overall, we can replace this equation of the equation number 5, because we need to discuss all the parameters from the arguments given in the last section about the capacitance, that I just give the arguments about the capacitance, that it CV can't be changed and the product can't be changed, Q is equals to CV. So again, using all these, keeping all these parameters that I just argument, or these arguments in mind, we can say the integral of this equation has a 0 value at time frame 0. This is the integral of the flux linkage. Actually, flux linkage is equals to flux linkage prior to the time period 0 time, that is constant, plus present time. 0 to present time is actually, we are saying that at time 0, when we are just going to turn on the switch, the flux linkage has 0 value, because we will discuss why actually, but keep in mind V has finite, not infinite. If you have a finite voltage, suppose that we have 5 volt system, so this is what I just want to show you, how its answer is 0. So 0 to time period t of this integral voltage, if we have a voltage, let's suppose 5 volt, we have 5 volt system, and we want to integrate it with respect to time t, and we wanted to discuss at any time interval, but right now I said that at time, especially when we are switching our system at time t is equals to 0, its value is overall system, this integral value will be 0. So let's discuss. If we have a 5 volt system, integration of this 5 dt, separating excluding this 5 from the integral because it is a constant, and integral of 1 dt, that is t. Now we are ready to apply the limits into this system. As we are only interested in the lower limit, because I said that at time of the switching, which means t is equals to 0, so 5 into 0, overall your flux linkage is 0. Suppose we have a system at t is equals to 0, the flux linkage is 0. So this is the overall proof, you can say, why we said that the flux linkage at time t is equals to 0. If we choose the, if we close the switch for a very short interval of the time, we have the approximately same flux. So this is the next assumption you need to make in your mind, that if you close the switch, if we close the switch for a very short interval of the time, we have approximately same flux. Like that, if I close the switch, I proved that already here, I proved that if we close the switch at time t is equals to 0, the flux value is 0 at any voltage, but it must not be infinite. But now I'm saying at time is equals to 0. Now we said that flux linkage is 0. At time is equals to 1 second, it is still 0. I am saying actually this is not exactly 0, but it is very close to 0. So that is the main reason we are saying it is not changing, it is still 0. So we can say that if we close the switch for a very short interval of the time, we have approximately same flux that is before the switch. Overall flux depends upon the flux that is prior to the switching time period, that is standard. I said that not standard, sorry, that is constant, sorry, I said that it is given to you, plus this 0 to t. At time t0 or just after some intervals of the time, very short interval of the time after closing the switch, this is 0. Understood? This term is 0 and this is given to you. So the flux is equals to psi naught, that is overall already before present in the system, nothing new after the switching very short interval of the time. So this equation becomes psi is equals to psi naught. Psi naught, what is psi naught? Psi naught is actually minus infinity to 0 time, means all the time that is prior to our switching, before the closing switch, and it is given to you and it is a constant and fixed value. So we can simply write that psi naught is equals to constant because it is provided to you. So this overall equation, this equation in the box becomes psi is equals to a constant value, any value, we are not interested. We can simply say that from equation number 4, there is a result in the equation number 4. What is hidden message in the equation number 8? There is a message that all the flux linkage in a system is constant for time t is equals to 0 and after time t is 0, very short interval of the time after switching. So this is 0. Not sorry 0, constant. The above equation actually states that the flux linkage cannot be changed instantaneously in a given system. As in case of the capacitive system, we would define that the capacitive system cannot be changed instantaneously. So here again we are defining that the flux linkage cannot change instantaneously in a given system. This principle is known as a principle of the constant flux linkage. So this is called principle of the constant flux linkage. Remember this in your mind. We will use this later on, that what is called the principle of constant flux linkage. This is called principle of the constant flux linkage because the flux before the system and the flux after the system is constant for a very short interval of the switching. After the switching still it is constant. So this is the called principle of the constant flux linkage. So if we have two systems like mutual inductance, let's suppose, sorry, not mutual inductance, I'm sorry, this is same system, sorry, this is the picture of the system that is prior to this turning on or prior to the switching, I1 L1. Suppose it has a fixed value I1 current and L1 is the inductance, fixed inductance. After some moments it is, let's say we said that it is now after we turning on the switch, after then it is I2 and L2. Then what happens? Subscript 1 refers to the time just before the system, as I discussed already. System 2 refers to the system after it is altered, mean it is on. So psi 1, so overall the flux linkage is equals to Li, because it is the same system, as I said that the flux linkage right now we are interested in the same system. So we are interested in the same system, means the single system. That is why I'm using there Li. If there is a two system mutual inductance, then we can replace this L with M. So psi 1 is equals to L1 I1, psi 2 is equals to L2 I2. For a very short interval of the time, we say that the psi 1 is equals to psi 2, means the system before the switching is the same conditions after the switching. L1 I1 is equals to L2 I2. This is called equation number 9. Remember this equation is very important and overall result. The principle of the constant flux linkage is similar to the principle of the conservation of the momentum. Constant flux linkage is the system in terms of the electronics or electrical systems, while the conservation of the momentum is the same principle but in terms of the mechanics, because sometimes it is very hard for us to find the is to visualize changes in electrical system. So then we go towards the mechanical system, then we refer to the mechanical system, and the same principles actually there. Then it might be sometimes helpful for us than understanding the system. So for whom it may concern that the principle of the conservation of the momentum states that if an object collides with the other, the total momentum before the system of the two objects is the same after the collision of the objects. Actually the momentum doesn't change, the main thing is momentum. So then sometimes we refer to our electrical systems when it is so hard for us to find a solution, or it is not easy to visualize a system, or it is not able to understand a specific problem. Then sometimes we convert the situation into mechanics and then take a look at this, it is sometimes it is easier to understand the and find a solution for the students. So electrical circuit is sometimes connected with the mechanical system, as the Newton force law states that Newton force law is actually the Newton's second law. Remember that, keep in your mind. Don't search on internet Newton force law, you might not find, it is very hard for you. But if you search Newton's second law, you will easily get this equation, that which states that the rate of the change of the momentum of any body, of suppose a body, is directly proportional to applied force. It means if you are applying a force on a body, that is directly proportional to the momentum. Here, this is the derivation form, F is equal to d over dt mv. Here m, what is m? M is your mass, F is your force, V is the velocity. MV product is called actually momentum. So in case of the mechanics, you can see this is a rocket, it is going in a constant velocity. Its velocity is disturbed if its momentum is actually disturbed. How it is keeping it in a specific and a constant type of velocity? There are the reasons. Momentum of the system cannot change instantaneously. Keep this in mind. This law valid for this system. In a system such as missile, where the mass is lost as a function of the time, actually it continuously the mass is reducing of a missile, because its fuel is continuously burning, and now its waste is its fuel is wasting in the form of burning. It is used and its weight is reduced. Velocity must be changed in such a way that the momentum remains constant. If the momentum doesn't constant, it is changing in such a way that momentum is varied, momentum is not constant, then it is very hard for us to achieve the targets. So this is the law that is applied on the missiles too. So there are the number of the conservation laws. Let's define that. We already discussed, or we discussed right now, till now we discussed 3 important conservation laws. First one, Q1 is equals to Q2. This is for the case of the charges in a capacitive system. When we define C1 is equals to C1 V1 C2 V2, there is a condition that I must not be infinite. Then we discussed the flux linkage, where the flux linkage in the inductive system is constant before and after some intervals. The limitation for this system is that your your voltage must not be infinite. Like L1 I1 is equals to L2 I2. So third one is belong to the mechanics, conservation of momentum. P1 is equals to P2, and the here important thing is your force must not be infinite, which means that if the momentum before the system is constant, after the system M1 V1 is equals to M2 V2. So this is the end of another episode, that is the episode 12. So let's discuss the further discussion from now. Okay, important thing I just wanted to discuss here. This is the end of the second very important topic, that is the conceptual scheme of the inductive system. Before this, keep in mind we already covered the capacitance systems, and now we discussed the inductive system, and now maybe in the coming episode we will further discuss the inductive system with the help of a practical case or with the help of an example for the better understanding. So let's discuss the next time, and we will meet inshallah each other in the coming episode. Take care. Allah Hafiz.